Thank you everyone for coming tonight. I'm really excited to be doing this. A little bit of an introduction about me before we get started. I was once in your seat. I'm a CDU alumni. I'm doing my master's degree here in engineering. I'm studying machine learning. I've worked in missile defense, and this past summer I worked at Microsoft as a software engineering intern, and I plan on going back after I graduate in the spring. So the reason I decided to do this was because I'm researching machine learning, and I don't think there's a lot of great resources for learning about neural networks for undergraduate students. So I really wanted to host something and maybe practice teaching a little bit too. So we're going to be building a neural network from scratch in Python. So let's get started. So before we begin, there is a textbook that you can read if you need extra help with the material, but you won't need it to follow along with any of the seminars. So all you really need is a laptop and Python, and that's it. So this is a book we'll be learning from. It's called Neural Networks from Scratch in Python. It's a really great textbook. It's like $30 if you guys want to pick it up, and if you're interested for extra detail. So a quick note. I think neural networks get a really bad rap because a lot of people in the computer science world think they're like so extremely complicated and hard to understand. And they're just a little vague, like nobody actually knows what they do. All we know is that they work. So yeah, I think it's good to acknowledge that they're one, complicated, and two, I don't know everything there is to know about neural networks, so I'm learning along with you guys. And three, don't get overwhelmed. We're just gonna break it down into really simple steps and learn about the most simple parts one step at a time. So let's talk about what we're going to learn today. So we're going to go through a quick history of neural networks, figure out where they came from, why they exist, and what they do. And we're going to talk about what a neural network actually is, what it's composed of, what kind of parts it has. And then we're going to talk about neurons, which is the most fundamental building block of a neural network. And then we're going to end by actually making some neurons. So I'm kind of excited about that. So question, how many of you have heard of neural networks? Anyone? Anyone? Okay, cool. Does anyone know where they come from? Okay, cool. Let's talk about it. So a little bit of a history lesson. Neural networks were first proposed in 1944 by Warren McCulloch and Walter Pitts. They were researchers at the University of Chicago who later started the MIT Cognitive Science Lab. So one of the, I think, the interesting things about neural networks was that they really just started as an idea. Nobody actually knew how to use them for the first 20 years of their invention. They were just like, oh, I think this could work eventually. But since the computers were so bad in the 1940s, there wasn't really anything they could do about it. And they were really just building on some ideas that Alan Turing proposed in one of his books. So honestly, it took until about 2010 for neural networks to become popular. And that was kind of when GPUs and some of the hardware you need to really train neural networks first became readily available to lots of people and cheap enough to actually use. So neural networks are actually based upon the structure and functionality of biological neurons. So think about your brain. So biological neurons have dendrites, they have cell bodies, they have axons, they have a nucleus and axon terminals to connect to other nuclei, right? In a neural network, we have neurons, and each neuron has a single number going into it, and they really just spit out different numbers. So one thing to note is that neurons in your brain can either be on or they can be off, but neurons in a neural network can represent any number effectively. And we'll talk about that a little bit more as we get into the lecture. So what is a neural network anyway? That's the question of the hour. So before we begin, can you think of any examples of neural networks? Anyone? Does anyone know where a neural network can exist in today's technology? Teslas, yeah, self-driving. That's a great example. What do you guys think of when you hear machine learning? What comes into your mind?
AI.
AI, yeah. So yeah, as you said, self-driving. That's a great example. I would say some people say like Terminator, which is not as great an example because AI is not that scary yet. And better yet, if you tell a mathematician, they might say, oh, it's something like this, which is true, but don't let that scare you because it's not that bad. So the reality of neural networks is both incredibly exciting and also kind of not at the same time. Does anybody know what that robot is or where it came from? Okay, so recently Tesla hosted an AI day where they introduced their Tesla bot. Basically, all this robot can do is walk a little bit, and it taught itself how to walk, which is the cool part, but it doesn't really look that exciting when you compare it to some of the Boston Dynamics robots that can do like backflips and that kind of thing. But the interesting thing here is that it taught itself how to work, so just how to walk. So just remember that. The bottom example here is from a company called Google DeepMind. Google DeepMind is leading some of the best research in AI today. And this is one of the recent papers, which is called Alpha Tensor. Basically, it figured out new math that no one has ever figured out before, which is really cool. So the current state of AI is interesting because we get some really interesting papers and ideas and inventions, but we also get like the Tesla bot, which barely knows how to walk and doesn't really seem that impressive on the surface. So something about neural networks is that they represent a really small subdomain of artificial intelligence. Not that small, but artificial intelligence is a huge, broad category of things, and neural networks just represent a small part of that. So within artificial intelligence, you have machine learning, which is itself a broad field. You have neural networks, and then you finally have deep neural networks, which are special neural networks that are really big and especially tuned for specific tasks. So neural networks can be really simple. We're going to be focusing on simple ones since we're building them from scratch. As you can see here, this one has what, like 12 neurons. It has what we would call an input layer, a hidden layer, another hidden layer, and an output layer. And we'll get into what those mean. But just know for now that each of them, like I said, contains a number, and that number we will be learning how to tune, basically. So neural networks, notably, are comprised of lots of different layers, and each neuron has the responsibility of communicating a signal to the rest of the network. This again ties back to the idea of a biological neuron, right? Because each neuron in your brain is connected to other neurons, and they're responsible for firing different neurons within your brain and telling you things, basically. So something to know here is at the beginning of the neural network, we have our input layer. Whenever you want to train a neural network or send it data, this is where the data starts out. So if you had an image, for instance, each pixel in the image would start out as one neuron within a layer, and it would travel through the network until it reached the end of the network, which is called the output layer. The output layer is responsible for telling you what the neural network thinks is going on. So whichever, like say this neural network is attempting to classify pictures of dogs or cats. So if it thought it was a dog, it would highlight maybe the top node, and if it was a cat, it would highlight maybe the bottom node. So I actually have a picture that goes along with this. So this is kind of what it looks like, right? It basically learns how to represent a specific pattern in data, and then it highlights the nodes that correspond with that specific image. So as it gets input data, the neurons basically turn on, and when they represent a specific pattern, they activate the neuron at the end of the network. So, okay, that was a lot. Are there any questions so far? Does anybody want to ask anything or clarify anything? If not, no worries, we can move on. But I want to make sure there's time for questions as well. Cool. So, the big question, what are neurons and how do they work? So each neuron has a list of inputs. So when I say neuron, just look at one of these tiny circles. It has a list of inputs. An input is just a line. So each neuron has lines that are going into it. This neuron right here has two inputs because it has two lines. Every input has a weight. So a weight is just a number. And every neuron has a bias. So just think of, every time I say input, weight, or bias, just think it's a number, because that's all it really is. So we're going to quickly talk about what the equation for a weight and bias looks like. As you can see here, it's really simple. What is the equation for this line right here? Does anybody know? It's y equals x, right? You're going to have to excuse my bad handwriting. So when we tune the weight of the neuron, all we are doing is adjusting the slope of the output of the neuron. What is the equation on the right? Who knows that one? Okay, good. You guys took algebra? Good. Okay. Pretty easy so far. So that's kind of what we're going to be doing today. When we look at neurons and we look at coding them, we're just going to be looking at how can we adjust the output of each neuron. Because when we have a neuron, we are giving it inputs, right? Each input has a number as its weight, so that could be 0.5, this could be 0.3, this could be 0.7, and then they all go into the neuron, and then at the end of it, it does some math in here, and it outputs a number, say 0.5. And we'll look at how that happens, but that's basically all that's happening here. So one further complication, not really that complicated, is when we add a bias. Not really a whole lot changes, but if we look at our equation, y equals x, basically the bias is just shifting that output up a little bit. So this is just added onto the end. So that would be plus 2 if you added a bias of 2 to that neuron. If you subtracted, it would just look like minus 0.7, right? Pretty simple so far. And that's really, gotta be careful. That's really all it takes to set the mathematical value of each neuron. I think one thing that's kind of interesting about neural networks compared to our brains is our brains don't have these like complex mathematical functions inside them, at least that we know of, right? Our brains just go, okay, it's either on or it's off. There's no math happening within our specific neurons in our brains. This can be thought of as a step function, kind of just a side note, but interesting to think about what are the differences between a neural network and our brains. So to reiterate, each neuron just has weights, it has bias, and that just comes out to a single number, which is the output of the neuron. So weights and biases impact the output that the neurons represent, but what math is actually applied to them to change the values. So we will talk about this more later on, but it goes through a couple phases. It goes through something called a activation function, and then it computes something called backpropagation. And we will talk about these more in depth later on, but just know for now that each neuron in a neural network contains just one number, and that value changes over time depending on what kind of data you give the neuron. So without machine learning libraries, deep learning neural networks, it's kind of scary, right? It looks maybe a little something like this. I don't think any of you want to code this from scratch because it would be awful and it would take you years. And since neural networks can have millions or even billions of weights and neurons, no one would ever do it, right? So that's why modern machine learning libraries have been invented, is because this is terrible, no one understands it, and it would take way too long to code. So what we've talked about so far is we've kind of talked about simple neural networks. We've talked about what they look like without machine learning libraries. And we've kind of shown what the equation for a neuron is. Any questions about any of this so far? Pretty straightforward. Okay, cool. So how do we code individual neurons? Let's talk about that. By writing some code. So if you guys would like to open your laptops and open your favorite Python editor, we'll get started on that. PyCharm. Yeah, it's the best one. Yeah, so if you guys do not have an IDE, I highly recommend PyCharm. It's my favorite Python editor, but VS Code works, whatever you want. You can write it in Microsoft Word for all I care, but that'll make your life pretty hard, so I would not do that. Okay, is everyone kind of generally ready to write some code? Okay. Okay, cool. So the first thing we're going to do is we are going to import NumPy. I always do it as NP because that's simple. If you don't have NumPy, you can just go pip install NumPy, and it should install for you within like 30 seconds or so. It's really easy. Actually, I'll leave that up there so you guys can see that. Okay, so the next thing we're going to do is we're going to import matplotlib, and we probably, actually, I don't know if you guys need to do that. That's fine. So those are kind of the only two libraries we're going to be using. We're going to keep it really simple, and actually we're not even going to use NumPy for the first couple lines of code. So we're going to start by coding just a single neuron here. So let's talk about what a neuron looks like, right? So when I was talking before about neurons, what components do they have? Does anybody remember what each one had? So they have one input, and each input has a weight. Yeah, correct. And a third mystery thing, each neuron has a bias, right? Cool. So let's start by creating an array of inputs. Is everyone familiar with arrays in this class? Okay, cool. I was hoping the answer was yes.
Some of the freshmen may not have had it yet.
Oh, that's true. They're in C++. Okay, cool. So we're gonna create a neuron with 3 inputs. That's all this is. If you guys haven't seen Python before, it's super simple. It's like reading pseudocode basically. So what you're seeing here is just an array contains 3 inputs, and we're also going to create an array of weights. So we're just going to randomly set these. We'll say input 1 has 0.2, input 2 has 0.8 as its weight, and input 3 has negative 0.5 as its weight. This is kind of just randomly set. If you're using real data, obviously that would set the weights. And then to begin with, we're going to set the bias to 2. Normally, our bias starts off at 0 because it has no conception of what the weight looks like yet. But since we're kind of just messing around here, we'll set the bias to 2 just so you guys can see. Okay? So that's a basic neuron. It has 3 inputs. Each input has its own weight, which is its value. And then our neuron finally has a bias. So how do we put this together? So the equation we are going to use is the output of a neuron is just equal to the weight of the input plus the bias. Pretty simple stuff. So the way we implement this in code just looks like this. So we're going to go inputs at 0 times weights at 0. So for anyone that doesn't know, when I'm saying 0, arrays in Python are 0 indexed like most languages, and 0 just refers to 1 right there. Thank you. So we are going to do this for each layer here. So we're going to go inputs at 1 times weights at 1 plus inputs at 2 times weights at 2. And then what do we add at the end? Bias, right? Plus the bias. Okay, and then we'll just add another line down here and we'll say print output. Cool. Okay. So when I hit enter on this, it's gonna basically give us the value that's contained within our neuron. So let's figure it out. Okay, 2.3. Now obviously that doesn't really mean anything in this context, but that's how every neuron within a neural network works. It adds up all the weights from each input, and then it adds the bias at the end, and that's the output from the neuron. So let's talk about how we build on this. What if our neuron had another input? What would we have to change about what we've written so far to accommodate a new input? Does anybody know? What would we have to add? Okay, we'd have to add another input. There's one more thing we'd have to add. Another weight, right? Because each input has its own weight. Would the bias change? The bias would not change. Each neuron only has one bias, and that's just added at the end. So if we wanted to add another input, we would simply do, let me copy that over. So we would just simply say 4. And then someone shout out a number. What should I set the next weight to? 7? Okay, good number. I don't know if that really goes with the trend, but it works. Okay, and then what would we have to change about our output? Who knows the answer? Come on, you guys are smart.
Add another line.
Okay, add another line, right? Easy. Inputs at 3 and weights at 3 and add the bias. Easy stuff. So as you guys can probably tell, if you want to create a neural network and you want to make it bigger, you're just adding more lines to your code, right? It's pretty simple. Obviously, if you had a neural network with 8 million neurons in it, you're not going to want to code all of them individually. So we'll get how to optimize that in a little bit, but that's basically it, right? That's how a neuron calculates its output. And our new value, thanks to our addition of 7, is 30, which is, I'm sure, a nice number. Okay, so obviously that was really simple. How do we make this more complicated, right? How do we do something cool? So let's talk about adding more neurons. How do we build a layer of neurons? Because obviously a neural network's not a neural network if it only has one neuron. Then it's just a function. So if each neuron has to have its own set of weights, what do we need to add to our code next? We need to add weights for each function, or for each neuron, excuse me. So if we want to add let's say we have 3 neurons in our layer, we're going to need 3 separate weights. So if you just copy your weights and paste 3 times, if my paste will work, let's see, there we go. We can call this weights 1, weights 2, and weights 3. Again, the values within the weights, they don't matter that much, since we're not using real data yet. All that matters is that we're understanding what's going on between the connections and why they have to have this number of weights. So something I think that I glossed over a little bit in the presentation was that every neuron in a layer of neurons is connected to every neuron in the previous layer. So if one neuron has 4 connections, then every single neuron in that layer will have the same number of connections. They're all connected to each other. So we actually do not have to change our inputs at all. Every single neuron we use here will just be connected to the same inputs, and they all have the same values. So I have some predefined weights here that I'm just going to copy over to change the values. And then since we added 2 more neurons, we also need to add new biases. So if you guys want to add 2 more bias variables, these are good ones to use.
Can I ask a quick question?
Yeah, of course.
Your inputs are 1, 2, 3, 4. Those are not indexes. Those are the values that are being entered from those 4 nodes from the input layer.
Yeah, so that's actually a great question. So the inputs actually just refer to which neuron that the previous weight is coming from.
It's not the value?
It's not the weight. The weight is the value. Right.
Okay.
Right. So if I'm going to turn on the lights really quickly so I can kind of draw you guys a picture of what's going on. So before we carry on, let's just imagine what we're doing a little bit. So since we have 4 weights, basically it just means we have 4 neurons in our imaginary previous layer. We haven't coded this layer, but we're just imagining it as our inputs. What we're creating right now is a layer with 3 neurons. So this right here is the layer that we're creating. And each one of these is just connected to every neuron, right? So this is what we would call a deeply connected neural network, because each neuron in the previous layer is connected to every neuron in the next layer. So these 3 neurons right here correspond to our weights 1, 2, and 3, and our inputs correspond to these 4 neurons. So that's kind of a nice way to imagine what's happening in the code. And then, of course, we have our bias variables, which just go in here. Okay, so this is where things start to get a little gross in the code. So please bear with me. We are simply going to go up. Let's copy our output layer from the previous cell. And then we are basically going to add our new neurons to this layer. Formatting doesn't matter too much, but we basically just need to add our code here. So input stays the same, but this will change to weights 1, weights 2. I think this is why people stop doing it manually. Okay, I'm getting a bunch of errors, but you guys get the point. We'll see if this runs in just a second. Yeah, that's right. And we have to change our bias variables, of course, because each one has a different bias. So let me fix my indentations so Python's not mad at me anymore. Let's see here. All right, this is supposed to be a bracket. Okay. So that is, let me add some commas, right? So an easier way of representing this is basically just saying, okay, this is neuron, don't actually type this, but this is what we just created. We basically just created an array with 3 neurons, and we set our output variable equal to that. So when our output variable actually calculates, we get the output of all 3 neurons. And instead of a single number this time, how many outputs do we get? 3? Yeah. Yeah, because we just calculated the output of an entire layer. So we get, output, there we go. Okay, yeah, we get an array of values. So this is obviously neuron 1, neuron 2, and neuron 3, and that's how we calculated the values for each one. Okay, so to quickly debrief, what we just created is a fully connected neural network because each neuron is connected to every input in the previous layer. Imagine what it would be like if we had to code 1,000 neurons. Obviously, this is not pretty, and this is kind of where NumPy comes in. I wanted to take you guys through the process of building a neural network from scratch because it's interesting and helpful, and all of you will at one point interface with machine learning in your careers. And this will just kind of give you a solid foundation to understand what you're actually doing when you're calling machine learning methods, because you won't actually have to do this in practice. So what we're going to do next is we're going to optimize this a little bit because the previous code is obviously not good. So if you will code with me, we're going to create a new input layer. We'll call this 1, 2, 3, 4. And we are going to create a new array of weights. So importantly this time, our array of weights is going to be a 2-dimensional array, and this will store the weights for all 3 neurons. So if you guys want, you can copy your weights from up above and just put them down here and just basically insert them in. And that gives us our new weights. I'll wait for a second so you guys can catch up. Okay. So once we have our 2-dimensional array of weights, we need to create an array of biases, however you prefer to pronounce it. And this will have 2, 3, and 0.5. And those are our biases for our neural network. So at this point, you might be wondering, okay, why are we creating 2-dimensional arrays? What's the purpose of this? Don't worry, the code is about to be much better, you'll see. So we're going to use a classic for loop here. I'm sure all of you have heard of for loops. And this will make our lives way easier. So we're going to say for neuron weight and neuron bias in okay, so before I proceed, this is really easy. So we're going to iterate through both neuron weight and neuron bias at the same time. So both of these arrays, and we're doing this by basically combining them into a nice small package. Python has a really great method called zip, which basically just allows you to loop over both of them at the same time. And since biases and weights both have 3 entries, technically, it allows us to do that. So it's really easy. So we're going to set an output variable to 0. Uh-oh. If I can spell output. I guess my education didn't help me that much. Okay. So we are going to add one more for loop to this, and then we're pretty much going to be done. So for neuron input and weight in, we're going to call zip again, inputs and neuron weights. We're just going to add the individual output for each neuron. So this is, again, it's just the input times the weight. Really easy. Okay, cool. Is everyone with me so far? Any questions? Okay, cool. I'll let you guys type for a second, and then we will figure out how to print the output. Okay, so the last step is, of course, to add our bias, because every neuron has a bias. So for each neuron, we will add its associated bias, which we just get from the top of our for loop, right? Because every time we step through our for loop, we just move one index forward in our bias array. So we're going to add our bias, and then finally, we are going to add our results to our output array. I think this is supposed to be a list, actually. For some reason I set this to 0, but I think that's supposed to actually be just an empty array. Yeah, sorry about that. Thank you. Okay, and then at the end of this, we're just going to print our outputs from every layer. Cool. So once we print this, we should get, the same result we got last time. Okay. What did I do? Neuron weights is.
I think the neuron weight needs to be weights.
What line? Oh, right here. Float object is not iterable. Oh, right, because this actually is supposed to be 0. I see. Okay, I led you guys astray. You're going to have to forgive me for that one. Okay. Layer outputs is not defined. Let's see where. Oh, right. Here we go. Okay, I figured out my mistake, guys. Please add that variable to above the for loops so that we can actually append to it in our for loops. Okay, so this should hopefully work now. Okay, cool. So I think we changed our values a little bit, but this is the same idea as what we happened last time, right? But instead of just individually incrementing and adding together every single input and every single weight for every neuron. We just did it using a for loop. This is obviously way better, but some of you might be thinking at this point, okay, that was just as much work to program. What's the point of this? And I will show you really quickly because I think it's an important point to understand. So if we just copy this, right? And let's say we pasted this twice. So we just tripled the size of our weights, and we do the same thing with our biases. The really great thing about this is that if it all goes correctly, this should still work, right? It should scale, and yeah, exactly. It iterates. We didn't change the value, so the output is the same, but it's 3 times as much. And all we had to do in this instance was just add our values to our weights and biases array. If we did this up here, we would have had to code, this many more lines. And then it starts looking something like this. Obviously, that's not great, and we want to eliminate as much garbage code as possible. So that's why we want to use for loops. And Python makes it super easy with its zip function. Yes, of course, just find it, sit anywhere. Okay, so at this point, the code is still not great. We're not even using NumPy yet, so let's talk about how we can use NumPy to make this even better. So to demonstrate, let's create 2 new arrays. We'll call one A, and this will just have 1, 2, and 3. And we'll create a second, and this will be called B. This will have 2, 3, and 4. So what we're going to do here is demonstrate a really, really critical fundamental piece of machine learning, which is that in order to get the results we want from machine learning, we need to use something from matrix algebra. Some of you have taken linear algebra, but probably most of you are familiar with the dot product. So dot product is just A0 times B0 plus A1 times B1 plus A2 times B2. That's it. So we're just multiplying our arrays together. Let's print this out at the end. That just gives us our answer, 20. So this is really important because this is just the output of a neuron. Imagine A as our inputs, and imagine B as our weights. We just calculated the output of a neuron. This is, again, really important because it allows us to make our code much easier to read, much more efficient, and we can optimize it finally. So let's go back up. Let's just copy our original inputs and weights and our original bias, and we'll use that with NumPy. Okay, 1 second. Okay. So instead of writing all of the array multiplication code that we had at the beginning, we can simply import NumPy. If you guys haven't done it, again, it's just import NumPy, and I like to name it MP just because it's a little easier to write. So let's calculate our new output. So our new output is just simply the dot product of these two plus the bias at the end. So we give it our weights and inputs. And then at the end, we add our bias. And this is exactly the same as this. That's what we just did in one line, what took 4 before, right? This is the 2 differences. One is really easy to read, and one is a pain to type out. So if we print our output here, we get the same answer, exactly what we would expect. Actually, let me change that to outputs, because that's printing from the previous cell. Okay, exactly what we got at the beginning, 2.3. Perfect. So what if we wanted to apply this to a layer of neurons like we did? So let's take our example, 3 neurons, for instance. if we go back up here, let's copy our biases, our weights, and our inputs. And then let's optimize this using NumPy. So basically I just took, let me clean this up a little bit. We're just taking this. That's all we have. Okay, so in order to compute this with NumPy, it's ridiculously easy. You guys are going to be angry that I made you code all of that array algebra before this because it's really like sadly easy in NumPy. So if we just create a variable called layer outputs again, we'll set this to np dot product, and then we'll give it our inputs. We'll give it, and so, okay, here's one small tricky part. We need to convert our weights to a NumPy array. A NumPy array is just a simple data structure that NumPy uses that it helps it understand things. And basically, we're just converting our weights into an array that it understands. So we'll call this, we'll give it weights, and then we'll say .t. So an important part of dot product is that you have to do something called transpose your matrix. And transpose is really easy to understand. So when you transpose a matrix, you're just switching the rows and the columns. So it's a little bit more useful than that, but just for right now, think of transposition as switching the rows and the columns. And then at the end, we're going to add our biases. And we are going to print our layer outputs. And we should hopefully get our values again. So if you guys don't remember, this code right here is functionally exactly the same as this code. So this is why we don't want to code everything manually. And this is why we're using NumPy, because, man, without it, we would be here for a couple more hours at least trying to do this. And yeah, so we can just use NumPy. We can calculate the dot product. We can just give it all of our weights and all of our biases, do a little fancy transposition trick, and that's it. We get the same values. So that's actually all the code that we are writing today. Let me turn on the lights so I can see you guys. And that's actually kind of the end of learning things today, because neural networks are so complicated. I don't want to overwhelm you guys with a bunch of math and a bunch of random things on the first lesson. So what we did today was actually really cool. Let me go back to the PowerPoint, and I just have a couple more slides. So, okay, good. We wrote some code. Here's what we created today. We created our first layer of neurons. And I think these values are a little bit different than what we ended up using, but this is what we created. So just like I drew over here, these are the inputs from the previous layer of neurons, and this is the output for each neuron. And that's what we just coded in those last 4 lines of code that we used the dot product on. That's all it took to calculate the output. And the nice thing about this is this technique scales to an infinite number of neurons, right? If you had 1,000 neurons, if you had 1,000,000 neurons, the code would look exactly the same. And we're going to continue to build off that in next week's lesson. Just one final note is this is the equation for dot product if you guys haven't seen it. It's pretty straightforward. I don't really recommend doing it by hand too often unless you're, unless you really love math, but it's pretty simple, right? We're just taking the sum of 2 products, in this case, because we have 2 by 2 arrays, we're adding them together, and it's giving us our output. So let's talk about a summary of today's work. Today, we learned about the history of neural networks and who created them, why they were created, and why it took so long for them to actually start being used. We learned what a neural network is and how it's not as scary as you might think it is, and some of the math behind neurons. And we talked about the structure of neural networks and the individual networks they're composed of. And we finished by coding individual neurons, and then we built a small layer of neurons at the end. So that's all I have for you guys. But yeah, thank you for coming tonight. I really appreciate it.
So announcement. Next week.
Yes, so next week we'll be talking about activation functions and I think back propagation a little bit. So it's really exciting. Before you guys know it, you'll be able to have a neural network that tells you whether something is a dog or not. So very exciting stuff. We'll use some real data next week. It'll be exciting. Thank you for coming. How's it going? Good. Oh, okay. So I can send you PowerPoint and I can edit it out. You send me. Yep. Thanks for coming. Thank you. No worries.